Okay, so we are recording. So for this last chapter, right, we finally made it. We're at the last chapter. We're going to be looking at intermolecular forces. So as I had kind of mentioned, we're going to take a lot of what we did in the past two chapters with Lewis structures and then going into Vesper geometry and understanding whether the molecule will be polar or nonpolar. We're going to do that and now add to the intermolecular forces. So first thing is intermolecular forces versus intramolecular forces. So in the last chapter, we were looking at intramolecular forces, so forces within the molecule. Now what we're looking at are the forces between the molecules. So what are the forces that hold molecules together? So for example, why does water stay in the liquid phase at room temperature and other substances are solids and other substances are gases, right? Methane is a gas at room temperature. That's CH4, and that has a molar mass of about 16 grams per mole. And water, only a little bit heavier, 18 grams per mole. That's a liquid at room temperature. So those are the things that we're trying to look at with this chapter. Then we're going to look at intermolecular forces as it relates to boiling point, melting point, heat of vaporization, vapor pressure, some other things. And we have a nice mathematical formula for us to use called the Clausius Clapeyron equation. So that's sort of an overview. And just real quick, we'll look at phase diagrams. So first, intermolecular forces. When we're looking at solids, liquids, gases, covalent compounds for the most part, we won't be looking too much at ionic solids. We did that in a previous chapter, but we won't be looking too much at ion size versus, what the charge is, +1, +2. We touched on that previously. So that's not going to be a big thing here. We're going to be looking at mostly covalent compounds, which is why the Vesper is going to segue right into us or into this chapter. So first thing is our three forces. We have dispersion. We have dipole-dipole forces. And then we have hydrogen bonding. Those are the three. All right, and they're additive. So dispersion forces are in all molecules. All molecules have dispersion forces. So that's sort of like a baseline. That's in everything. Dipole-dipole, those forces are only in polar molecules. So a polar molecule will have dispersion forces and dipole-dipole forces. So they always are additive. Hydrogen bonding is when the hydrogen itself is bonded to a nitrogen, an oxygen, or a fluorine. It has to be one of those three. So hydrogen to a carbon, no hydrogen bonding. It has to be hydrogen bonded to a nitrogen, oxygen, or a fluorine. And if you can imagine, these are fairly electronegative. So those compounds are going to be polar. So when you have hydrogen bonding, again, those compounds will have dispersion. They're polar, so they're going to have dipole-dipole forces. And then in addition to that, they have hydrogen bonding. All right, so they're always additive. So anything that has hydrogen bonding has polarity and dispersion forces. If something is polar, it has dispersion forces and dipole-dipole forces. So what's the difference? Dispersion forces, these are in all molecules. And the way I kind of thought of it was, it's the way that the electron sort of cloud or distribution is dispersed across the molecule. So even if you have a non-polar compound, because those electrons are constantly in motion, at some instantaneous point, the electron distribution is not even, right? Because the electrons are just constantly moving. So at some instantaneous point in time, there might be a negative end and a positive end in this molecule. But the problem is it just always keeps moving, right? The electrons are just constantly moving, moving, moving. So it's not even in a circle. They're just always moving, moving, moving. So in an instant, you can have a negative end on the molecule and a positive end on the molecule, but an instant later, it's corrected itself, right? So this is called an instantaneous dipole. All right, so instantaneous dipole. So it only lasts for, just that spare moment in time, right? And then it'll fix itself, and then the electrons will get off balanced again in another instantaneous dipole, and then it corrects itself, et cetera, et cetera, et cetera. So what this does is if you have a neighboring molecule where at some point in this molecule, the electrons are on the right side, in that instant, we've got an electron rich negative side and an electron poor side. what that can do is create sort of a domino effect. And in the neighboring molecule, the negative here can push the electrons away and also create an instantaneous dipole in the second neighboring molecule. And then if you imagine the third neighboring molecule, the same thing. So it creates this instantaneous dipole. And when the positives and negatives line up next to each other because of the electron rich side and the electron poor side, right, that creates an attractive force. So in that instant, you have molecules that are attracted to each other, but then in the next instant, it goes away. So it's not a very strong intermolecular force, but it is an intermolecular force. And like I said, it's in all compounds. All compounds have this possibility for the instantaneous dipole. So if I'm looking at two compounds, how would I know which one has higher dispersion forces or lower dispersion forces? And typically what we check here is we look at the molecular weight or the molar mass of the compound. And the idea here is, and this makes total sense, that the higher the molecular weight is, the more electrons there are, right? Because that means the more protons there are and more neutrons generally as well. So more electrons, that means more likely to have an effect with that instantaneous dipole, right? The bigger the molecule is, the better that impact could be by the instantaneous dipole. So the heavier the compound is, the higher the molecular weight or molar mass, the more electrons there are, the more impactful that instantaneous dipole can be. So higher molecular weight means higher dispersion forces. The other thing that you can look at, and honestly, this is more of a thing for organic chem. So I kind of like, hey, I mentioned it, but we're not really too worried about it, is if you look at a carbon compound, you can have, like, for example, your carbons can be in a straight chain, or they can be like in a T structure, right? So when they're in a straight chain, right, a nice long, I think, they refer to it as an elongated chain. This actually will do a better job at creating an instantaneous dipole because it's sort of spread out, and that can do better at the neighboring molecule in terms of kind of rotating those electrons by an instantaneous dipole. So elongated is also going to have a higher dispersion force or a higher impact from that instantaneous dipole than something that's, in a T shape. Now, we don't really look at that too much because we don't look at organic structure until we get to organic. So I have to mention it, but that's really we're not going to really worry about that until we get to organic. So for dispersion forces, all molecules have it. If we're only talking about nonpolar compounds where dipole-dipole isn't an option and hydrogen bonding isn't an option, then if we're comparing two nonpolar compounds to figure out which one has the higher dispersion force, we basically look at molecular weight. That'll tell us what we need to know. And there's an example in the notes where we look at the halogens. So for example, we look at F2 versus I2, and I can tell you that one of those is a gas at room temperature and one of those is a solid at room temperature. So if it's a gas, the intermolecular forces must be pretty weak because nothing is holding that together, right? The fluorine molecule, well, I gave it away. The molecules are very independent, right? They're in the gas phase, they're spread out. We learned with gases that the assumption is they have no attraction for each other. So in the gas phase, intermolecular forces are very low. When we go to liquid and solid, especially now, intermolecular forces must be really high because we're holding those molecules together. So when I look at the F2 and the I2, both of these are nonpolar, right? We can imagine that single bond holding the fluorine together. Electronegativity difference between the two fluorines is 0. So that's the classic nonpolar compound. I2, same thing, nonpolar. So if I look at those two, the fluorine has a molar mass of 19 times 2, so about 38, where the iodine is 126 times 2, so 252, right? So in terms of the molecular weight, the iodine is much higher molecular weight. Okay, the F2 molecular weight, pretty low. All right, and so what we can see is that the iodine should be the solid at room temperature, whereas the F2 is going to be the gas. All right, and so weak intermolecular forces, which I always abbreviate as IF for the F2, and the iodine, it still only has dispersion So all I will say here is that it has stronger dispersion forces. And that is an intermolecular force, right? That is one of our 3 intermolecular forces. So that's what we look at with dispersion is we basically focus in on the molecular weight if we're comparing 2 compounds. There's nothing else going on here. There's no polarity, no hydrogen bonding. So we're just looking at 2 compounds that only have dispersion forces. If we're comparing those 2, we look for the molecular weight. Like I mentioned, fluorine's about 38, iodine about 250 something. So when I look, the iodine being a much higher molecular weight, that means there's a lot more of electrons, that instantaneous dipole much more impactful. So that can hold the iodine better together, right? So higher intermolecular forces means more likely to be a solid. Very weak intermolecular forces means more likely to be a gas. All right. Now, the next type of intermolecular force we have is only found when you have a polar substance. So F2 and I2 won't have this. This is called a dipole dipole, which is nice. It sounds like polar, right? So the dipole dipole force, what you're looking at here is, let's say I had an HF bond, right? Let me use carbon because that might look confusing with hydrogen bonding. Sorry, let me do carbon. I feel like that's not showing up very well. Sorry, let's do a carbon fluorine bond. So we learned back in intro that if we're just looking at a bond, right, we can say that the bond will be polar if the electronegativity difference between those 2 elements is greater than roughly about 2. And fluorine is our most electronegative element. So we know it's going to pull the electron density, that shared pair of electrons, closer to the fluorine side, creating an electron-rich side. And then the carbon's going to be an electron-poor side. And when I touched on this in intro just really briefly, I had said, okay, we're not worried about the curvy D thing. We talked about this earlier in the semester as well, but that D is what the dipole, that's the symbol for the dipole. And again, the negative side is going to be on the more electronegative element, the positive on the less electronegative element, because this bonding pair of electrons is being pulled towards the fluorine. Now that was looking at a bond. Then what we did in the last chapter is we looked at an entire compound. So this doesn't quite work here because this is just one single bond. So if I look at a compound, let's say I've got CH3 and then an F, right? Then there's my fluorine. So what we learned in Vesper was that the CH3F or the fluoromethane would be a tetrahedral shape. And it's AX4, there's no lone pair on the carbon. But because of that fluorine being so electronegative, we're going to have a negative part of the compound or molecule and then a positive side. All right, the electrons are going to be pulled towards the fluorine and nothing in the opposite direction, right? Nothing to kind of counterbalance that. So this is going to be overall a polar molecule. And so that means that this fluoromethane would has the dispersion forces, right? Because that's in all molecules, and the dipole dipole because now it is a polar compound. So both of those intermolecular forces are present in the fluoromethane. So when you have a polar compound, you're adding to the dispersion forces that are already there. And when you have an electronegative element in there to kind of throw things off, like fluorine, oxygen, chlorine, right? If it's not being counterbalanced by equal fluorines on all the other parts, right, on all the other terminal elements, then we learned that in the last chapter that'll create a polar compound, and that means there's going to be dipole dipole forces. And so now instead of just this instantaneous dipole, like in that instant there's a positive and a negative end, this isn't in an instant, this is permanent, right? When I look at that compound, that does not change. Because fluorine is so electronegative, it will always have, the lion's share of the electrons being pulled in that direction, and that creates that negative end versus the positive end, the electron poor side with the carbons and the hydrogens. So that right there is not just in an instant, that's permanent, right? So this is a permanent dipole rather than an instantaneous dipole. And then that makes sense because it's permanent, it's much more impactful. So it's going to definitely create higher intermolecular forces, higher forces holding those molecules together when the positives and the negatives can line up, right? Electrostatic forces are some of the strongest we have in nature, right? Positives and negatives, they love to organize. All right, then the last one is if you have hydrogen bonding, And that's only going to happen when hydrogen is bonded to a nitrogen, oxygen, or a fluorine. And water is like the best example here. So if I look at water, we've got our two lone pairs on the oxygen, which is why it's an AX2E2 bent molecule. So we learned when we were doing our Vesper that this would be a polar molecule because we've definitely got an electron rich dipole on the electronegative oxygen and then electron poor on the hydrogens. And so what actually ends up happening only with hydrogen bonding is the organization structure of it is so unique. The hydrogen actually sort of partially bonds to another oxygen, right? It loves that lone pair. So what happens is you get this like highly organized structure where the negatives and positives line up, but it's beyond that. It's not just what we had with polar. The hydrogens actually kind of partially bond to two different oxygens. It's almost like the electrons kind of rotate. And so you end up with a very specific, tight, really strong intermolecular forces holding those compounds together because they're like the molecules actually partially bond with one another. That doesn't happen over here. This is just plus minus happy because they stabilize each other being next to each other. This is actual partial bonding between the molecules. So that's why this is so special and such a high intermolecular force. So not only do we have dispersion because all molecules have dispersion, we also are polar. So we've got dipole dipole forces here. And then we've got the hydrogen bonding where the hydrogen partially bonds to each oxygen in two different compounds. So hydrogen bonding, when we have that, those are our strongest intermolecular forces, which is why water with a molecular weight of only 18 has a relatively high boiling point. And it's just such an amazingly strong molecule, right? I don't know. I think I remember in grad school, somebody asking me, you know, what's your favorite compound? And I'm like, I know this is not going to excite you, but it's water, right? Like if you know enough about intermolecular forces, water is an amazing thing. Plus, you know, you got to have it to live. So it's kind of special. So I'm going to look at a few compounds and go through kind of what we did in the last chapter or two, tie that into intermolecular forces because it really is connected. And then we'll start talking about, you know, how that relates to boiling points and heat of vaporization and other things from there. But that's the beginning. Those are our three intermolecular forces. So we are going to start with Sf4 sulfur tetrafluoride. All right. And what I want us to remember here is when we did this, we had the sulfur with a lone pair expanded the octet. And then we had fluorine on four of those, four fluorines attached to the sulfur. This was AX4E, which is seesaw. And if we were trying to figure out what type of intermolecular forces we have here, we know, again, baseline, we always have dispersion, but this should be a polar compound because of that lone pair, right? We remember that the bond angles are always to sort of maximize the distance between the bonding pairs of electrons and the lone pairs of electrons around the center sulfur. And if we ever have an E, with two exceptions, right? But if we typically have an E, that means that we're not counterbalancing that with a pull. Like you have normally, like with the fluorine, you have a pull and then you have an opposite direction pull. So you can end up being non-polar. I'll show you that example when we get to it. But the lone pair is something we look for to say, oh, okay, this is also going to be polar. So we're going to have dipole dipole forces here as well. All right, so two intermolecular forces in the sulfur tetrafluoride. Next compound is carbon dioxide. And if we remember this one, we've got a carbon center, two oxygens attached with a double bond. So this is AX2 linear. And there's no lone pair on the carbon. And because the two terminal elements are both oxygen, overall, this should be a non-polar molecule, right? We have a pull towards the oxygen and a pull towards the other oxygen. And because both of those terminal elements are the same, overall, that should be a non-polar molecule. So the only thing we should have here is dispersion forces. And as we know, carbon dioxide is a gas at room temperature. That always suggests that we have pretty weak forces when that happens. Now, if we look at HF, All right, that one I can just go ahead and draw the structure. There's no geometry here to worry about because there's only two elements. So obviously it's going to be linear. And so it's a nice, easy molecule to look at. We know that the fluorine, highly electronegative. So you're going to have definitely a polar molecule, right? So we know we have dispersion in the HF because that's in everything. We know we have the dipole dipole. But the hydrogen bonding, what we look for is when hydrogen is bonded to either a nitrogen, oxygen, or fluorine. And we have that position here. We've got hydrogen bonded to a fluorine. So we also will have hydrogen bonding here, right? And so for something with such a low molecular weight, right, of only 20, like neon, for example, molecular weight of 20, definitely a gas at room temperature. HF is a liquid. All right. Okay, so oops, I maybe did that too quickly. Sorry. Two more. We've got ICl5. All right, so iodine pentachloride. So we've got the iodine and the 4 chlorines, or sorry, 5 chlorines. All right, so we kind of start out in that octahedral shape of 6 total groups, but because one of those bonding sites is a lone pair site, this is where you have your square pyramidal. All right, and it's an AX5 with the lone pair on the iodine. So again, this is going to be polar. And so that means that we're going to have dispersion forces and we're going to have dipole dipole forces. All right. And then the last one here, this is one of those exceptions, the Xef4, the xenon tetrafluoride. So in this one, if you remember doing this one, you have 2 lone pairs on the xenon, and then you've got your 4 fluorines attached. So it's, again, it starts out as an electron geometry of octahedral, but the more specific molecular geometry here is AX4E2, which is square planar. And what we talked about with this one was, this is the one exception, one of the 2 exceptions when you have a lone pair, typically that's going to tell you that you have polar. But since the fluorines are in a plane, one is pulling this way, we have an opposite pull right in the opposite direction. Then the fluorine going up and to the left, and then you got a fluorine down and to the right. So this actually works out to be non-polar. All right, that was one of the 2 exceptions. The other one is the AX2E3, which turns out to be linear. So in this one, the xenon tetrafluoride, you only have dispersion forces. All right, so what we're going to do then is now connect that with understanding what our boiling points are, right? So when does that happen? And so when I was talking about HF just a little bit ago, I just always thought this was so interesting. So if I have HF and I have HCl, the boiling point of HCl is a negative 85 degrees Celsius. And the boiling point of HF is right around room temperature, so about 20 degrees Celsius. So that is hugely different, right? For a molecule to become a gas at negative 85 degrees Celsius versus a molecule to become a gas right around at room temperature, or sorry, liquid gas, that transition happens right there. So it'll either become the boiling point, right? It turns from liquid to a gas, that's boiling, right? We know that. So that transition, depending on which way you're going, right? Cooling it down or heating it up. As you heat it up, it turns into a gas at negative 85. And then the HF liquid right around at room temperature, but turns into a gas right around at 20 degrees Celsius if you're heating it. So why so drastically different for 2 things that look like they should be pretty similar? In fact, the HCl is a higher molecular weight. Chlorine is heavier than the fluoride. So when we look at this, we know they both have dispersion forces because everything does. We know that they're both polar, right? Because we've got an electronegative halogen. So we definitely have a negative end and a positive end on both of these. So they're both going to have dispersion forces. So when you look at that, you think, why are they so drastically different? And that's because of the hydrogen bonding that happens in HF that doesn't happen in the HCl. So it's just kind of interesting because, like when we were talking about the halogens, when we were looking at F2, Cl2, Br2, and I2, right? The fluorine is a gas at room temperature, the chlorine is a gas, the bromine is a liquid, and the iodine is a solid. But in that scenario, we only have dispersion forces. So molecular weight is what sort of predicts what happens with the intermolecular forces. So with these, right, the HF and the HCl, if you were kind of looking at that in the same way, thinking about molecular weight, you might have chosen this backwards, right? So the intermolecular forces that come into play, you really have to think about the structure of the compound and what type of forces you have. And in these, the halogens, right, this is just dispersion forces. So all we could do is look at molecular weight to form any kind of trend. But when we look at the HF and the HCl, both of them are dispersion forces, both of them have dipole dipole. So what predicts this huge difference in boiling point is the fact that the HF has the hydrogen bonding. So you just have to kind of look at your molecule for a second and think about what type of forces we have. So that kind of combines what we did in the last couple of chapters with the new material. So one more here. I'm going to tell you we've got two compounds. Let's say one of them is boron trichloride and the other one is nitrogen trichloride, right? And those look like they should be roughly the same. And I'm going to say one has a boiling point of 160 degrees Fahrenheit and the other is 55 degrees Fahrenheit, right? So the temperature at which it boils is 55 degrees Fahrenheit versus 160. So again, like that boiling point, why it always goes to that is what we think about is when you start to heat those molecules that are in the liquid phase, they get excited, they start to move more, and eventually they have to get enough energy to break those forces holding the molecules together. And when that happens, it can go into the gas phase. So boiling point, and we'll talk more about that in a minute, is when that transition happens. So the higher the intermolecular forces are, the higher the boiling point will be. So when I look at those two compounds, they really look like they should be about the same, right? Boron trichloride, nitrogen trichloride, boron and nitrogen, almost right next to each other on the periodic table. But what we have to think about is what we learned in Vesper. With boron trichloride, remember that's one of our exceptions to the octet rule. So boron trichloride is actually AX3 trigonal planar. All right, and because there's no lone pair on the boron and all terminal elements are the same, that means that this is a non-polar molecule. And I'm sorry, I probably should have tried to make that a little bit better in terms of the 120-degree even bond angle. So even distribution of the electron density there with those three bonding pairs, because all of those chlorines equally offset each other. AX3, no E, non-polar, all we have are dispersion forces. With the nitrogen trichloride though, now we've got that lone pair on the nitrogen. And then if we remember here, we've got a trigonal pyramidal shape. This is the one where it's like in a little pyramid because of that E on the nitrogen. So in the nitrogen trichloride, now what we have is like an electron-rich bottom and an electron poor top, right? So we're pulling the electron density down, but not up. So this is going to have polar forces as well. So this is dipole forces as well. All right. So when I look at my boiling points, then the one that is non-polar, right? Those are always the weakest because they don't have the dipole forces. They don't have hydrogen bonding. It's just dispersion forces. So this BCl3 should have the boiling point of 55 degrees Fahrenheit, right? It should boil sooner, right? With less heat. It needs less heat energy to overcome those intermolecular forces. With the nitrogen trichloride though, now because of that permanent dipole, the boiling point here is going to be much higher. It's going to take much more energy to start breaking up those intermolecular forces. So this kind of goes back to what we did with thermo when we looked at bond energies. And if you break a bond, it's endothermic, where if you form a bond, it's exothermic. The forces work the same way. If you break the intermolecular forces, you have to put energy into that. So we have to heat water to boil it, right? So anytime you want to take something from a solid to a liquid to a gas, you've got to break intermolecular forces. You have to put heat into that. So endothermic processes. If you go in the opposite direction from a gas to a liquid to a solid, like we learned in Hess's law, when you reverse the reaction, what was endothermic is now exothermic. So as you create intermolecular forces, right, going from a gas, ordering them into a liquid, and then ordering them into a solid, energy is going to be released. Those are exothermic processes. Okay, so that is sort of the thing that we want to overview kind of with intermolecular forces. So we've got our 3 intermolecular forces. All right, so we have the dispersion forces are the weakest. When we get to the dipole dipole, the reason why these are stronger is because it adds to the dispersion forces. And then when we get to the hydrogen bonding, these are the strongest because it adds to the dipole dipole forces and it adds to the dispersion forces. So all 3 forces are present in compounds that have hydrogen bonding. So I'm going to draw like a little line here and say, okay, this is increasing intermolecular forces, IF. All right, so what happens, right? What are the trends that we can look for? Well, the ones that we've been talking about is we're going to see increasing boiling point. If we look at compounds that seem like roughly similar in size and molecular weight, but we're changing from dispersion to polar to maybe include hydrogen bonding. If we looked at 3 compounds, we're going to see an increase in boiling point as we go and we add those intermolecular forces. That makes sense. Again, the idea is in order to reach boiling point, you have to put enough thermal energy in to break those intermolecular forces. The higher those forces are, the higher the energy is going to be needed, higher the boiling point. The other thing instead you could have here is the melting point. So if you're just looking at solid to liquid versus liquid to gas, it's the same idea, right? You're still causing an endothermic process to occur. It's going to need more energy if the intermolecular forces are stronger. The other thing that we're going to be looking at though is heat of vaporization. So that is delta H. So that's our enthalpy vaporization. That one's going to come up in the Clausius Clapeyron. So sometimes they'll ask you questions about heat of vaporization, but it's the same trend. The energy required to go to vaporize something, right? Liquid to a gas, makes sense. The stronger the intermolecular forces are, the more heat will be required. So there's an oddball here though, and it's when we talk about vapor pressure. So I'm going to give you 3 compounds. We're going to look at propane, which is C3H8. So we've got 3 carbons, and then on those carbons, we have 4 bonds total. And all of those sites right there are hydrogens. So there's 8 hydrogens attached. That's propane. Then what I can do, and this is a little intro to organic, is propanol, which is basically the same. Prop means 3 carbon chain, and these are all hydrogens. But on one of them, we put an alcohol group, not a hydroxide, it's alcohol. So we have this OH group, that's all like when you see xylitol, sorbitol, those are alcohols. So that's the OH group that we've got there. So we've got our 1, 2, 3, 4, 5, 6, 7, 8 hydrogens still, but now we've added that oxygen in the alcohol group. So we have C3H8 and then O, but sometimes it'll be a structural formula and it'll be C3H7OH so that you can see what the structural formula is, right? So 1, 2, 3, 4, 5, 6, 7, there's my C3H7, and then there's the OH. So sometimes they'll write it that way. Then there is propanoic acid. And that oic acid in organic means that you have a carboxylic acid. So prop still means you've got 3 carbons. The carboxylic acid is this functional group here, carbon double bonded to an O, and then you've got, again, that OH group here. And what's interesting is this is not a base. This is actually an acidic hydrogen. So it's kind of makes you say, well, that's different. That's not what I learned about OH. All right, so these are all kind of similar in size, right? They're a 3-carbon chain, but they're very, very different. In terms of boiling points, you could look them all up. They change drastically as you kind of move through that. And so if I look at, the intermolecular forces here, propane, again, carbon, hydrogen only bonds. This is the classic non-polar compound. So the only thing we have here are dispersion forces. But when I get to this OH group, the alcohol group, or the carboxylic acid group, because that hydrogen is bonded to an oxygen, now I've got dispersion because that's in everything. It's polar because of that OH group, right? The oxygen pulls the electron density towards it. So dipole dipole forces. And the big one is the hydrogen bonding. All right. And so propanoic acid, same thing, has dispersion, but also dipole dipole. All right. And hydrogen bonding. So if you were given these 3 compounds and they say, okay, which one has the highest intermolecular forces? Well, we can definitely rule out propane, right? And we can look at the propanol and the propanoic acid. And you're kind of like, well, they both have dispersion. They're both polar. They both have hydrogen bonding. Then what you default back to is the molecular weight. And what you would see is, because the extra oxygen here, the propanoic acid has an extra oxygen, has a higher molecular weight. So we assume this to have the highest intermolecular forces. And along that, right, which one has the highest boiling point? We expect propanoic acid. Which one has the highest melting point? Propanoic acid. Which one has the highest heat of vaporization? Propanoic acid. So all of those go together. There's one that's sort of the outlier and it's backwards. And the question will be, which has the highest vapor pressure at room temperature, RT? So if I had propane, propanol, propanoic acid, just in a container sitting on the counter, a sealed container, which one would have the highest amount of vapor pressure? And, melting point. Yeah, sorry, Grace, MP is melting point. So solid to liquid. The vapor pressure, right, that what we look at is basically if I had a sample and I've got a liquid here, the vapor pressure are the gas particles that build up right above the liquid phase. So when you get into Chem 2, you do a lot about what's called dynamic equilibrium. So molecules are constantly in motion. So some of the liquid molecules are going to vaporize and turn into a gas. Some of the gas molecules condense and go into the liquid phase. And they're kind of constantly moving around. And dynamic equilibrium is when the forward reaction and the reverse reaction are happening at the same rate. So it doesn't actually look like anything's happening, but molecules are always happening, right? So this vapor pressure is the amount of gas particles that build up in the gas phase, like right above the solution. And what we can sort of know going into this is propane is a gas at room temperature, right? It's the gas for your grill. So this should definitely have the highest vapor pressure because it's all in the gas phase. So what you want to kind of think about here is it's opposite from what we were looking at before. Normally, highest intermolecular forces meant highest boiling point, highest melting point, highest heat of vaporization. But the highest vapor pressure is when you have the weakest intermolecular forces. And that I think makes sense, right? The weaker those forces are holding the particles together, the more likely we're going to be transitioning into the gas phase, right? The more gas particles we're going to have because the forces holding the molecules together are very weak. So the one that has the highest vapor pressure is the one that has the lowest intermolecular forces. So of those 3, it should be the propane. So if we're looking back at our scale up at the top here really quick, when you have increasing intermolecular forces, that means increasing boiling point, melting point, heat of vaporization. And it also means that you're going to have decreasing vapor pressure. So you might see that as well, given a list of compounds, which one has the lowest vapor pressure or which one has the highest vapor pressure. Just remember, this one is backwards. So if it asks you for the highest vapor pressure, that means the lowest intermolecular forces. If it asks you for the lowest vapor pressure, then that means the highest forces. So that one is just sort of the opposite. All right. So of those three, propane with the weakest intermolecular forces should have the highest vapor pressure. All right. So some of the remainder of the chapter is actually just going to be thermo, just now looking at phase changes. So you're going to see some enthalpy calculations like we did. So that's going to look really familiar. That's going to be the next thing I talk about. Then we're going to do a phase diagram really quick to look at all the various phase changes that we have, because we've only really talked about boiling, of vaporization and condensation, but we've got others that we want to learn. And then the last thing will be to look at the Clausius Clapeyron equation, which is what our lab this week is going to look at. All right, so the next topic, the thermo part, this should seem familiar from when we did thermochem. No, it doesn't look up. There we go. All right, oops, too far. So question here says, the enthalpy of fusion, so that's a phase change we'll talk about in just a second, of sodium is 2.60 kilojoules per mole. Right? How many grams of sodium can be melted by adding 81.7 kilojoules to the sodium at its melting point? Sorry, that was supposed to be an N. So melting point. Okay, so with thermo, when you had enthalpy, right, it was like an extra stoichiometric factor. So fusion, when you see that, fusion is a fancy word for melting. Right, so fusion just means we're going to take the solid. So we're going to take our sodium solid and we're going to turn it into liquid. Right, so that's what the fusion, that is that phase change. Just like vaporization is taking a liquid and turning it into a gas, we call it vaporization. When we do solid to a liquid, we call it melting, but the technical term is fusion. So that would be our reaction process for sodium fusion, right? And our heat of that process is 2.6 kilojoules per mole. All right. And so we remember from thermo that if our delta H is positive, right, that means that this is an endothermic process. And that's what we talked about, that if we're breaking intermolecular forces from solid to liquid, that delta H should always be positive endothermic. What we also learned with Hess's law is that if I do the opposite of that, which is take the liquid to a solid, or, fancy word freezing, but they like to call it solidification, then the delta H should be negative 2.6 kilojoules per mole. So that transition, that phase transition right there, this is our heat of fusion for melting the sodium. Our heat of freezing or solidification, which is the exact opposite reaction, would have the same delta H value just with a negative. It would be exothermic negative 2.60 rather than positive 2.60. So a lot of what we saw in thermo comes back. We see it again here when we start looking at heats of phase changes. It's just now we're only specifically looking at a phase change rather than an entire reaction like we did in thermo. So I've got my thermochemical equation. And now what it says is I'm adding 81.7 kilojoules of heat, and I want to know how many grams of sodium. So what we talked about was the delta H here, that is a conversion factor. So I'm adding 81.7 kilojoules. I know for every 2.60 kilojoules, I'm going to be able to melt 1 mole of sodium. And then if I want to know grams, right, that's where my molecular weight comes in, or molar mass from the periodic table, which is 22.99 grams. And so that hopefully looks familiar, where we just use that delta H as a conversion step. So we know that if it's 1 mole, it's 2.6 kilojoules. Since I have 81.7 kilojoules, I can do a total of about 31 moles of sodium. And then if I multiply that by the molar mass, I can get my total grams. And to 3 significant figures, it would be 722 grams of sodium that I could melt with that 81.7 kilojoules of energy. All right, so hopefully that looks familiar from thermo. I know thermo's been a little time ago. All right, another kind of example here says condensing ammonia, nitrogen trihydride. And sorry, I should have said 25.7 grams of, so we got 25.7 grams of ammonia. It releases 35.3 kilojoules of energy. All right, what is the heat of condensation for the NH3? All right. And typically when we do our heats of vaporization, heats of fusion, all those delta H's that we remember from thermo, we're going to want our units in kilojoules per mole. So first, I always like to think of, okay, what is the phase change? Just so we remember. Condensation, right? That is the opposite of vaporization. So we're taking ammonia in the gas phase and condensing it into ammonia in the liquid phase. And we are trying to figure out what the delta H value is for this. That's what we want, our sort of our delta H constant. And what we have so far is that we know 35.3 kilojoules of energy is released. So it's a negative, right? It's going to be an exothermic process. And that is the amount of energy for 25.7 grams of ammonia. So the only thing we really have to do here is just convert grams to moles. So I go to my periodic table, molar mass 17.04 grams per mole for the ammonia. And then that's it. That gets rid of grams, goes to moles. So basically, I just need to know how many moles of ammonia I have. So I take my 35.3, divide it by the 25.7 grams, and then multiply it by 17.04, and I get a negative 23.4 kilojoules per mole. So now from there, I have my thermochemical equation, right? So if I take NH3 in the gas phase and turn it into NH3 in the liquid phase, that heat of condensation is negative 23.4 kilojoules per mole. So like we were talking about just a little bit ago, if I wanted to do the reverse of that, NH3 in the liquid phase, turning that into NH3 in the gas phase, instead of condensation, this is vaporization. And like we saw with Hess's law, when you reverse the chemical reaction, you just have to change the sign of your delta H. So instead of an exothermic process, which is the condensation, we now have an endothermic process, which is the vaporization. And it goes back to those intermolecular forces. When we take the liquid, convert it to a gas, we have to break those dipole dipole and dispersion forces that we saw with ammonia, right? The trigonal pyramidal has a permanent dipole. So we have to break those intermolecular forces and turn it into the gas phase, right? Where we say they basically have no attraction for each other anymore, right? Not always quite so right, but if they're pretty spread out, it works, right? So breaking those intermolecular forces, we've got to put energy in. When we take them from a gas to a liquid, though, they're gonna form those intermolecular forces, holding them together, and that's gonna give energy out. So this is a little bit of review of thermo, like what we saw, where we can use delta H as a conversion factor, like we did with the sodium example. We can solve for delta H if we understand the energy and the amount of substance we have. The only thing that's specific here is we're just typically looking at phase transitions rather than like an actual chemical reaction. This is just going to be a physical change. So again, reversing the equation means we change the sign, but understanding, again, whenever you form intermolecular forces, looking at this one, sorry, at the top, forming intermolecular forces, exothermic process, and then breaking intermolecular forces, energy has to be put in. All right. So that is the kind of the review from thermo. There will be questions like that. The next thing, looking at all of these phase transitions, right? We saw fusion. There's a couple more that we want to look for. So if we go from solid to liquid, we saw that that was called fusion or melting, but fusion is the technical term. Liquid to a gas, that's where we have vaporization. And if we take solid directly to a gas, this is called sublimation. All right. And all of these are endothermic processes, right? Breaking up intermolecular forces. The sublimation, the classic example there that I always use because it's familiar is dry ice, right? Which is just solid carbon dioxide. At Halloween time, right? We get our dry ice, it sublimates, turns into the gassy fog, right? So that's the process of sublimation. So the carbon dioxide, the dry ice doesn't go to a liquid first, it just sublimates, it goes right to the gas phase. So solid to liquid, melting, but technically fusion, liquid to gas, vaporization, and then solid directly to a gas called sublimation. So now let's do the opposite. If I take gas to a liquid, we saw that in the ammonia question, that was the condensation. If we take liquid to a solid, freezing, but technically they call it solidification. And if we take a gas directly to a solid, then they call this deposition. And I kind of thought of it like a gas is depositing on the becoming a solid. That's how I remembered it. But anyway, I don't know if that helps or not. So condensation, gas to a liquid, liquid to a solid, solidification or freezing, gas to a directly to a solid is deposition. And all of these, right, are going to be exothermic changes because we're forming intermolecular forces as we go. So they're all opposites of each other. You know what I mean? Like the fusion solid to liquid is the opposite of solidification, liquid to solid. Like we saw vaporization and condensation are opposites. Sublimation and deposition are opposites. So if I know the heat of sublimation, then the negative of that is the heat of the deposition for the same compound. So those phase changes, right, they're all kind of connected together, and we can see these on what's called a phase diagram. So phase diagrams are unique to a substance. Every substance has its own unique phase diagram. And so I'm going to just show you a very generic one at this point. So phase diagram, what you have on the y-axis is you will plot pressure. And then on the x-axis, you look at temperature. And so what we can kind of imagine here is that as we go across, right, as we heat something, we're probably going to transition from solid to liquid to a gas. But it depends on where we are in pressure and temperature. So you'll have an initial curve, and then you'll have like another curve, and then another curve, something like that. And again, every compound has a unique phase diagram. So they kind of generally look like this in terms of shape, but they're all different. So as I go across here, I can think, okay, low temperature, this is probably going to be my solid phase. As I increase temperature, that should be my liquid phase. And then if I keep increasing temperature, that should be my gas phase. This triple point, right? The point at which all three phases intersect, at that pressure and temperature, all three phases can coexist. So you could have a sample that had solid, liquid, gas all in the same container at the triple point. So what are the phase transitions that happen along each of those pathways? So right here, if I'm looking at this boundary, this is separating solid and gas. So this is your sublimation or deposition, right? That's your phase change right there for solid to a gas, sublimation. That's okay, Grace. Thank you. Grace, gas to a solid, deposition. This one here, right? Solid to liquid, that would be fusion. The opposite, freezing, or like I said, solidification. And then liquid to a gas, I'm just going to write them both here, is condensation or vaporization. So these are those curves. So it'll tell us, phase diagram will tell us, like if we know the temperature we're at and the pressure we're at, we can cross-reference this and say, oh, okay, we would have a liquid at that pressure and temperature, whatever it is. So a lot of times with phase diagrams, just to start, this is what they'll do is they'll give you a phase diagram and they'll say, okay, they'll label the points, like this is A, B, C, and D. And they'll say, okay, what's happening from B to D on this line right here? What phase change is occurring there? So you would just have to know solid, liquid, gas. Going from a liquid to a gas means we're either, depending on if we're heating it or cooling it, right? We're either vaporizing it or condensing it. Or if it says, well, what's happening between A and B, those points there, that's changing it from a solid to a gas. So that's either sublimation or deposition, again, depending on whether you're heating it or cooling it. So just knowing all of your different phases, knowing which ones are endothermic and exothermic, that's really what we're looking at for that section. Now, the last section that I have to talk about is when we use the Clausius-Clapeyron equation. So Clausius-Clapeyron equation, it is ln of P2 over P1 equals our heat of vaporization over R, and then 1 over T1 minus 1 over T2. Now your book has it slightly different, and we saw this when we were doing Mcat, the Mcat formula. If you have the inverse of the initial temperature minus the inverse of the final temperature, then you don't have to worry about a negative here on the heat of vaporization. When you look at the formula in your book, they do T2 minus T1, and they've got a negative here. So I'm going to give you the formula so you don't have to worry about memorizing it, because it can make it hard when you see it delivered in two different ways. But I always liked this way better, because to me, it was always so easy to just like forget the negative. Even though this may come up as a negative, I don't know. I just liked it better without the negative in it. Okay, so where is this going to, like, what is this used for? So what this is used for is we can relate the vapor pressure of above a liquid sample, or just in general, the vapor pressure with temperature. We can connect that. And what we're going to do in lab is we're actually going to take the vapor pressure chart that we use for those collected over water problems. So we're going to use the vapor pressure chart of water. We're going to plug in different temperatures and pressures, and we're actually going to solve for the heat of vaporization. So we're going to find out what the heat of vaporization is. So that's one method you could use. Like if I know, for example, at 20 degrees Celsius, the vapor pressure is 100 torr, and at 30 degrees Celsius, it's 200 torr, I can figure out what the heat of vaporization is for that compound. All right, so there's a couple of different ways to do it. One of the ways that I think is, one of the questions I think is interesting to use this. So what we know about like being out at high altitude, if you've had any experience being out at high altitude, right, you probably have heard the air is thin. So if you're, out in Pikes Peak, Colorado, or Breckenridge or somewhere, and you're 15,000 feet up or wherever you are, right, it says the air is thin, right? So density is really low. There's not as dense of a abundance, I guess, of oxygen, right? So your pressure is a lot less. Your atmospheric pressure is less because it's not as dense, right? We have less molecular collisions. So just as out of curiosity, here's a question for you. So in Breckenridge, Colorado, atmospheric pressure is about 520 torr. All right, what would be the boiling point of water in that Breckenridge, Colorado? So rather than having to spell out Breckenridge again, I'll just say, what would the boiling point be in Colorado? The heat of vaporization of water, we need that, is 40.7 kilojoules per mole. All right, and we need to sort of know one other thing here, right? So we have a pressure and we want to know temperature. So we need something else here, right? We need like another pressure and another temperature. So boiling point, we need to talk about that. So we talked about boiling is when you go from a liquid to a gas. Okay, that makes sense. Boiling point, technically, the definition of that is when the vapor pressure above the solution equals atmospheric pressure. So what we're looking for in a boiling point is the temperature at which the pressure above that liquid sample, right, through heating it, the pressure above that is equal to the atmospheric pressure. So the other thing we need to know here is something called the normal boiling point, NBP. Normal boiling point, I wish they had called it standard boiling point, because then that would be like, oh yeah, that makes sense. So what we look at is what is the boiling point at standard pressure, right? Standard pressure is 1 atm or 760 torr. When we learned our boiling point of water, it should have been mentioned that is a standard boiling point, right? That is a normal boiling point. So when we were talking about the boiling point of water being 100 degrees Celsius, that's at standard pressure, 1 atm, 760 torr. So at 760 torr, the temperature of boiling, so that means your vapor pressure will be 760 torr. When your temperature is 100 degrees Celsius or 373 Kelvin. And just as expected, temperatures always have to be in Kelvin. So when we use this formula here with the Clausius Clapeyron, your temperature, as usual, always has to be in Kelvin. Pressure, it doesn't matter as long as the units match. So if they're both torr, great. If they're both ATM, great, right? But so it's kind of like gas laws where the pressure unit doesn't matter as long as they cancel out, but temperature, as always, has to be in Kelvin. So the normal boiling point of water, again, I prefer to call it the standard boiling point of water, is what is that boiling point at 1 atm, standard pressure, 760 torr. And we know water, it's 100 degrees Celsius, which would be 373 Kelvin. So if what happens, like when you go to high altitude and you go to boil water, because the atmospheric pressure is so low, it reaches boiling point at a much lower temperature. So that's why they'll have adjustments when you're out in Colorado. Like if you're looking at baking a cake or boiling pasta, it's different than when you're at sea level because that atmospheric pressure being lower means your boiling point is going to be reached quicker, right? If all we have to do is get to an atmospheric pressure of 520, we can do that at a lower temperature. So your pasta, your boiling water is at a lower temperature, which means it's going to take longer to cook, right? So we learned that in kinetics when we go into Chem 2, that if the temperature changes, the rate of the reaction changes. That makes sense because the molecules aren't moving as quickly. So what we want to sort of go in expecting is that at a normal pressure of 760, we know our boiling point is 373. If we lower that pressure, we expect boiling point to also be lower, but we're going to look and find out exactly what it is. And the Clausius Clapeyron will help us do this. Now, the other big thing about Clausius Clapeyron is the R. It's not the 0.08206 that we're used to. It is 8.31 joule per mole Kelvin. So it's a different R. All right. And again, that'll be given. So don't worry about memorizing it. The other big thing to pay attention to is that your heat of vaporization typically will be in kilojoules and your R is in joules. So just make sure that you convert one or the other to make sure the energy unit cancels out. All right, so I'm going to line everything up like I used to always do. So if I kind of pick my pairs, if my P1 is 760 torr, that's my standard, then my T1 is 373 Kelvin. If my P2 is the 520 torr, the T2 is what I'm looking for, right? I want to know what that temperature is going to be. And then I have my heat of vaporization. That was given in the question. It's 40.7 kilojoules per mole, but I'm going to go ahead and change that to joules. So 40,700 joules per mole, because then that will cancel out with my R constant. All right. And now at this point, I'm ready to sort of plug in, right? So I'm going to try to fit this on the screen. So ln of P2, 520 torr over P1, 760 torr equals my heat of vaporization, the 40,700 joule per mole, divided by the 8.31 joule per mole Kelvin times the inverse of T1 minus the inverse of T2. All right, and I don't know what T2 is yet, so I'm going to just label that as my X. All right. So here's what I was mentioning. Your delta H, right, almost always given to you in kilojoules per mole, but because the R constant is joules per mole, just make sure you convert that. So now joules per mole cancels out, and the per Kelvin will cancel out with the temperature over here. So that all will work out, because this is technically per Kelvin, but per, because it's in the denominator. So don't worry about it, but the Kelvin unit will cancel out as well. So first thing I'm going to do is this part over here. I'm going to take the 520 divided by the 760. And again, what I mentioned was the pressure unit doesn't matter as long as it cancels out. So if they were both an ATM, the ratio is still the same. So I'm really taking here the natural log of 0.6842. And then I'm going to go ahead and kind of do some division over here on the right side. So 40,700 divided by 8.31 gives me 4897.7136. And then I would have the inverse of 373, which is 0.002681 minus, and then 1 over x. Now with these questions, you have to kind of show your work on these, because if you round more than me, or you don't leave the digits in the calculator, then it can throw it way off. I mean, it can be a pretty big difference. So I try to leave everything in the calculator as much as I can. So first thing I'm going to do is I'm actually going to go back. I'm going to take the 520 divided by the 760, right? That was the 0.6842. Then I'm going to hit my natural log key. So that answer, this part right here, is negative 0.3794896. All right. And then that would be equal to, I'm just going to rewrite it step by step, 4897.7136, and then times 0.002681 minus 1 over x. So I'm trying to do it piece by piece in case you follow this later. All right. Now what I would do, because I have this answer right here in my calculator, the negative 0.3794896. Now what I would do is I'd go back, cross multiply the 8.31, and then cross divide the 40,700. So basically I just moved this over here. So I have negative 0.000077483 is equal to 0.002681 minus 1 over x. All right, and we're solving for x. So I'm going to have 1 over x. I'm going to add 1 over x to both sides so I can get rid of it over here. And then I would have my 0.002681 plus 0.000077483. All right. So on my calculator, I've got this answer still in it, the negative 0.00. Okay. I'm going to change the sign on it because I want to now add it to the other side. So I changed the sign, and I need to add it to the inverse of 373. So I love this calculator because it works just the way my brain thinks it should. So I'm going to hit add 373 inverse. Bam, there's my answer. All right, so my inverse of x is equal to 0.002758448. And then if I want to solve for x, I just need to take the inverse of that. So I take the inverse of that and I get 362. So my x is 362, and that is my temperature. So that's in Kelvin. All right. So essentially what happens when we get to high altitude and the air is thin, pressure goes down, my boiling point goes down. So I'm looking at a boiling point here. Instead of 100 degrees Celsius, I'm right around 89 degrees Celsius, right? Because if I subtracted 273, that's right around where I would be. So imagine you're doing a reaction in boiling water, but your water is only at 89 degrees Celsius rather than 100. Because the temperature is lower, the reaction's going to take longer, right? So that's why you always have these adjustments when you're at high altitude. So the math on these questions is kind of robust. I'll put it that way. I always loved this calculator. It's very nerdy for me to say that I love a certain calculator, but this calculator really matches the way my brain thinks about how to solve this problem. So it's I don't know. This is why I like doing this particular calculator. So I'm just going to show you it again really quick. So I'm going to take my 520, divide by my 760, enter. All right. So there's my ratio of my pressures, 0.684. Then I hit my natural log key. So that's where I got that negative 0.3794896. Now what I'm going to do is I'm going to cross multiply the 8.31. So times 8.31. And then I'm going to cross divide both sides by the 40,700. All right. So that's where this big number, well, not big, a lot of zeros, super small number comes from, negative 0.000077483. Now that's equal to, right, the inverse of 373 minus 1 over x. All right, the inverse of 373 was the 0.002681 and then minus my 1 over x. So this is still here and my minus 1 over x is still here. So I'm going to add 1 over x to both sides to get rid of it, right? Because minus, the opposite is a plus. And then I'm going to add this negative 0.0000777483 to both sides. So basically, I'm taking the answer that's in my calculator now. I'm going to take the negative of that because I'm adding it to both sides. And I'm adding that to the inverse of 373. So on my calculator, 373 inverse, bam, enter. There's my answer. So 1 over x is equal to 0.002758, da, 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 da. Then if I just want to solve for x, all I have to do is hit the inverse key and there's my answer. So I get, oh, technically, sorry, I should have paid more attention. It's 363 if I round up because of the 0.5. All right, and so that would get me at right around 90 degrees Celsius rather than 89, but we're kind of splitting hairs there. So with this particular math, if you don't keep all the digits, like if you just sort of round this to 4,900 and this is 0.003, your final answer is going to be way off. So try to be very careful about keeping all the digits for this one. I know it's a little bit of a pain, but it will really go askew. You'll really go sideways if it's if you don't keep all the digits. Try to keep as many digits as possible. So that's the Clausius-Clapeyron equation, but we can of course do more of it. I had another example question I was going to go through and I forgot to bring it over with me. So let me find it really quick. But I think Clausius-Clapeyron, you just need a couple of practice with a couple of the questions. Nope, that's not it. There we go. All right. Nope. Sorry, there was one more I wanted to do. Now I just have to find it. Oh, I think I rewrote it. All right. Okay, so here's a different question. All right. So I'll move this to the next page. All right, so we have a compound where the heat of vaporization, is 31.0 kilojoules per mole. And at 313 Kelvin, your pressure is 760 torr. All right, so this would be the normal boiling point of whatever this substance was, right? Because we're at a pressure of standard pressure. So that temperature would be the normal boiling point. So the question is, what temperature would we be at? I mean, let me actually change it. Let's do it another way. Let's ask this question. What would be the vapor pressure of this compound at 296 Kelvin? So right around room temperature. All right, so if we're kind of just throwing some things out there, when we were looking at water on the last example, the normal boiling point was 373. So what we can already know going into this is whatever compound it is, it has weaker intermolecular forces than water. We also notice the heat of vaporization is lower than what we had for water, right? And those two things go together. So again, just trying to tie intermolecular forces in with some of the general trends that we understand about what happens with intermolecular forces. So higher the intermolecular forces, higher the boiling point would be. Water has a normal boiling point of 373. This compound is only 313. So weaker forces and thus also weaker heat of vaporization. So we have our heat of vaporization for the compound. We have our normal boiling point. Again, that's the way it could be coded. It could say, this is the normal boiling point, 313 Kelvin. When it says that it's the normal or standard boiling point, that tells you that your pressure for that temperature is 760 because that's standard. Question is, what would be the vapor pressure of this compound or substance if I'm only at 296 Kelvin, right? So we still have our same formula. So that formula is going to be given, right? So don't worry about that. So we're going to have our ln of P2 over P1 equals heat of vaporization over R, 1 over T1 minus 1 over T2. All right, I'm going to say, okay, the heat of vaporization in kilojoules, right? We're going to go ahead and change that to joules. So not worried about sig figs here just for a second. We'll do that at the end. But 31,000 joules instead of 31 kilojoules. The R also will be given, right? 8.31 joule per mole Kelvin. So that'll work. We'll have that at the ready. And then just because I think it'll be easier to solve for P2, not necessarily, I just think I'll prefer that. I'm going to make the 296 my T2 because then that'll go with my P2, the unknown, right? So P2 is what I'm looking for. And then my normal boiling point up here, I'm going to make this my T1 and my P1 because those two go together, right? So the vapor pressure is 760 at 313 Kelvin. I want to know what is the vapor pressure at 296 Kelvin. And so now I'm basically ready to plug everything in. So P2 is my unknown. I'm going to say that that's my X. My P1 is 760 torr. My heat of vaporization in joules, 31,000. My R, 8.31, 8.31 joule per mole Kelvin. 1 over my T1 is 313. I'm not going to worry about the units. And then minus 1 over my T2, which is 296. All right. So on this one, I wanted to do it different than the last one because we're going to have to break up our P2 and P1 ratio. So you have to be careful with that because it's in parentheses and we've got a natural log function. You can't break it up without doing e to whatever, right? So because that is the anti of the natural log is the e. Okay, so because everything is here, I'm going to go ahead and do this part over here first. So again, on my calculator, I'm going to start with the parentheses. I'm going to take the 313 inverse, and then I'm going to minus the 296 inverse and hit enter. So this right here gives me an answer of negative 0.0001834.9. Now, because I've already got everything in the calculator, I can just keep going. I'm going to multiply this by 31,000. And then I'm going to divide that by 8.31. So all of this becomes negative, and don't forget the negative, 0.684500142. All right, so I've solved for everything on the right. What I have still on the left is the natural log of X over 760. So before I can break this up and cross multiply the 760, I have to, and your calculator will tell you, the opposite of the natural log is the E function, right? So I need to take E to both sides so I can cancel it out on the left. So on my calculator, I don't even have to retype anything. I just hit second ln. There's my answer. I got my E. So this is equal to 0.504342266. And now that's equal to X divided by 760. All right, and since I got rid of the natural log function, now what I can do is cross multiply the 760. So just times 760, and there's my pressure. So it would be 383. The unit would be torr, since it's the same unit as P1. So P2 would be 383 torr. So with these problems, it's easy to kind of go sideways. So sort of just from the math and hitting it into the calculator. So at the very end, just kind of go back conceptually to what you expect. We had a boiling point. Let me lower this. We had a normal boiling point at 760 torr, temperature was 313. We are lowering the temperature to 296. So there should be less in the gas phase. So we expect our P2 to be lower. Now, how much lower, we don't know. But if we had missed a negative in here somewhere, what we would have found is that that probably would have been the opposite. So you can always kind of go back and double check. Does that make sense? Lower temperature, we should have lower vapor pressure. All right, so on this one again, how I typed it in, and again, this is why I love this calculator. So I start with the parentheses. I took 313 inverse minus the 296 inverse, and then I hit enter. All right, and there's my answer. Now I'm going to go ahead and multiply by 31,000 joules, right? Divide that by that R constant of 8.31. So that was this number here. Now to get rid of my natural log function, I need to do the inverse of that. So the E, all right, there's my answer, 0.504. And now I can cross multiply the 760. And there's my P2, so 383 torr. All right, so that is everything. Well, most everything, I think, for this chapter. You're just there. I think there will be some practice maybe required with a lot of those Clausius Clapeyron equations, and we will be looking that in lab in a graphing aspect, but that'll come later in the week for my lab class. But that's it. Yes, 8.31 will be given. And so basically on the test, this right here will be given, the equation and the gas constant, or the cost, it's an energy constant that will be given. All right, any other questions for me? Sorry that it's not focused. I don't know why it does that. It sort of decides all of a sudden that it doesn't want to be in focus anymore. I'm going to stop and then start back up again, and then that usually does it. There we go. All right. If you don't have any questions for me, have a great rest of your day. But if you have questions for me, please let me know.